All right, so today we're going to continue on algorithms and algorithm analysis. We left it off last time describing what good pseudocode is, that it makes use of plain old English, makes good use of mathematical notation. I'll try to keep it as light as possible on mathematical notation, understanding that if you haven't had, say, 235 discrete math yet, you may not have all that notation. But it doesn't use any language-specific constructs. Right? It's not a Python code. It's not a Java class. It's not a C, function, etc. It provides the necessary details without providing too many unnecessary details. So it's Goldilocks, right? It's not too hot. It's not too cold. It's just right. And again, if I could give you rules for following to write pseudocode, then guess what? You have a programming language, right? So there's not any rules that you have to follow. They're just general guidelines. Remember that we are online, so if you have any questions, go ahead and post to Piazza or the YouTube live stream. The example that I think we put together last time, otherwise I'm just going to go ahead and fast forward here, is linear search, right? This is in the Computer Science 1 textbook, which is linked to on Canvas if you want to get a copy of it. But it's a linear search. Basically, it just starts at the beginning of an array or a collection. In this case, we label that as a collection because it's not actually an array. All right? It could be a set. It could be a dictionary. It could be a list. It could be an array, right? It could be anything. We do give that thing a name, though, and implicitly we say how many elements are in that collection. We also have this key element here, E sub k, right? Element, the key element, right? And then we clearly label the output. An element A such that A is equal to K. Now, did we say that this conforms to the equals because they're numbers? Did we say that this conforms to the dot equals method or the dot compare to method, and then we check to see if that's 0, right? We didn't put any of those details in because we want to keep this as generic as possible. It's kind of like writing parameterized code in Java, so that you can write one function that it can apply to any type. Well, this is at an even higher level. You write one algorithm that can be applied to any language, right? According to some criteria. And then we label it as phi if no such element exists. If this were C, I would return null, or a flag value like -1 because that's an invalid index, right? If this were Java, maybe I throw an exception instead. But here I'm just simply saying that we're going to return phi, right? A Greek letter phi. Then we have a for each loop here. For each element in the collection A, do the following. Note here that I am using these vertical lines because that is as far away as you can get from actual code as possible. This was typeset using LaTeX, so there are actually rules and syntax for typesetting this stuff. But ultimately, I'm making it look like nothing that is in any actual language. Okay, it looks kind of like Python in that Python is very light on syntax, but there's no colons, right? There's no indentation errors or anything like that you have to worry about. Instead, code blocks here are denoted by these vertical lines with an opening block and then an end keyword down here. For each element in the collection, we simply ask, well, if a sub I is equal to the key element that we're looking for, then we output it. We don't exit, we don't return, we don't do anything that is language specific. No semicolons, no curly brackets to denote blocks, etc., etc. And then in the event of an unsuccessful search, we output phi here. Right? Now, if we were to look at this from a complexity point of view, if we were searching for 42, right, then we would get lucky and we would only end up having to make one comparison. Right? That would be the best case scenario for linear search. If we got unlucky and we had to actually, we were searching for, say, 0, and we checked the first one, second, third, ... and found it at the last one that we were that last place that we were looking for, or we were searching for something that didn't exist, 1,000, right? Then we would still have to go through the entire array, right, making 9 comparisons to find out that it doesn't exist and return phi. That's the worst case scenario. In general, if there were n elements here, we would end up having to make n comparisons. On average, we could go ahead and, hand wavy here. We could average those two out, right? N plus 1 all over 2, which is roughly equal to n divided by 2. Right? And you would, if you did a more sophisticated analysis, you would eventually come out to the same thing, right? But I'll ask you, is that n divided by 2 versus n, right? Is that much of a difference versus? What's the difference between those? What kind of functions are those things? If I were to graph them, what would they look like? Come on. All right, there you go. All right, I'll graph n. What does that look like? Oh, here. Let me go in a different color. There's n. All right. What does n divided by 2 look like as a graph? Its slope is slightly less, but it is still a linear function, right? The growth rate of both of these is exactly the same, right? It's going to be some constant growth rate, okay? So, is there a big difference between these two? Well, yeah, in the constant sitting out front, but do we care about constants? Not in the long run, because all you need to do is upgrade your hardware to hardware that's twice as fast, and guess what? Now they're both divided by 2, divided by 2. So now one is divided by 2 and one is divided by 4, right? In other words, we want to look at the growth rate behavior of this stuff, right? And to do that, we need a more formal framework for doing algorithm analysis, okay? I'm going to give you a 5-step process. This is probably due to some old textbook or something, maybe even Levitin or something like that. But anyway, the first 2 steps are really easy, but are kind of nuanced. But they're going to be really easy if you write good pseudocode up front for your algorithms. 1, you identify the input. Well, guess what? If you write good pseudocode, the input is already identified for you, right? Where? Right there at the top, right? The input. 2, you identify the input size, n. And guess what? That's identified for us right there as well, writing good pseudocode. Now, there is some nuance here because, wait a second, we have a collection and a key, right? So there's actually 2 parts to this input, right? Which one do we focus on? Well, whichever one makes the most sense. 3, you identify the elementary operation. There's a whole lot going on with this algorithm, right? For example, if I were to actually implement this in, say, Java or Python or C or something, I would have a for loop that looks something like this, right? For int I equals 0, I is less than n, I plus plus. What's all going on here? Well, I've got the creation of a variable and an assignment, right? So 2 operations right there. Every for loop, or every iteration of this, I'm going to be doing a comparison, a 3rd operation. Every iteration, I'm also going to be doing an addition and an assignment. That's taking the value in one variable, incrementing it by 1, and then putting it back into that variable, right? I'm now up to, I'm losing the number of fingers that I have here because I'm now at least a dozen operations when you get down to the nitty-gritty. If you actually had to implement this, say, in assembly, right, it's going to be a dozen lines of code or something, right? Maybe. Right? So there's a dozen lines of assembly, there's a dozen operations, okay? We're also doing operations within that loop. We're doing a comparison here. If the element that we have to retrieve the element, we have to load up the element into some register, and then we have to compare that, and then we jump to a memory address or something. Right? I don't want to have to worry about those low-level details. Again, that's implementation-specific stuff. Take it to a different assembly language, and maybe you have a different number of operations. Take it to a faster computer, and each one of those operations takes half as much time, right? Transfer it to a slower computer, and now it takes twice as much time. I don't want to have to worry about that stuff. Instead, I only want to have to worry about one thing, an elementary operation, right? So keep it simple. When you're now, there could be multiple good choices, right? Comparisons are an obvious one. But sorting algorithms say we'll be doing swaps. So maybe swaps, you want to pay attention to that, right? There's no one answer, right? If you analyze it with respect to one operation, you will get one outcome. If you analyze it with respect to a different operation, you might get a different outcome, a different analysis, right? Neither one of them is wrong, necessarily. Right? 4, you determine how many times the elementary operation is executed with respect to the input size. And that's where the actual analysis comes in. If this is your elementary operation and it appears in a for loop, well, how many times does it execute with respect to the input size, right? Then finally, the last step here is that you're going to characterize the algorithm's behavior. That is, this function that you derived in step 4 using big O analysis. Okay. So now let's go through each one of these steps in detail using linear search here as our first example. Okay. First of all, we have to identify the input size. And again, this is going to be easy if you've written good pseudocode. It's generally given as part of the input, right, and clearly stated. But in some cases, the choice is not necessarily clear, right? In general, keep it simple. Focus on one input if there are multiple, right? So which one do you focus on, right? Focus on the most relevant input that may affect the runtime of your algorithm, right? The runtime or the analysis, whatever, right? So for this, let's just go ahead and get into it with an example, right? Linear search. Let's go back over here to my pseudocode here, and I've got two candidates here, right? The collection, which has n elements in it, and a key, which is only one thing, okay? So which one of these should I focus on? Which one is going to be more relevant to the actual algorithm that you're going to iterate over this stuff? Right? So is there a difference between searching an array of 5 elements and searching an array of 50 billion elements? Yes, right? The 50 billion, that's going to be way slower. So, from an intuitive standpoint, I'm going to focus on this one because it can grow, right? There could be 50 elements, there could be 50 billion elements. But there's only ever going to be one key. If I did focus only on this one key, guess what? The algorithm seems to be constant, right? It's no longer linear search, it's constant search, right? And that's not the case. We know that, right? So for linear search, it has 2, right? Linear search, the most appropriate input would be the collection. Collection, not the key. Not the key. Can't type today, sorry. I'll fix my errors later, right? Because it can grow, right, in size. But there's only ever one key. Right? What about another example here? Have you ever seen Euclid's GCD algorithm? So, all right, then let's look it up. Euclid's GCD algorithm in Python. Okay. Freecodecamp.com. Okay, I don't want this. I just want the pseudocode. All right, fine. Wikipedia. There we go. All right. I just want the simple version. Oh, come on. This is going to be a huge freaking article. All right. There we go. There. Very, very simple. It's a function that takes 2 values. These are integers, by the way, a and b. And then it goes into a simple for loop here, and it basically just divides, takes the remainder, divides until it finds the GCD. The GCD is the greatest common divisor. So if I have, say, 15 and 60, what is the greatest? What is the largest integer that divides both of those numbers? Well, 15 divides 15, and 15 divides 60. So what's the GCD? 15. If I have 77 and 21, what's the GCD there? Wolfram alpha. I said 77 and what? 21? GCD of 77 and 21. Well, 7 divides both of those. And I thought of that in my head because I was just making up prime numbers, right? 11, 7, 3, and 7. And I knew that 7 divided both of those things, right? So there's the GCD of those 2 numbers. What if they don't have any common divisors, right? I don't know, 97? Hopefully that's not, there we go. there's always a GCD of at least 1, right? If they don't have any common divisors, then 1 divides anything, and that's the simple answer. So what are the two inputs here? A and B. Numbers, okay? So Euclid's GCD algorithm takes 2 integers. How can we simplify that? Instead of considering both, only consider the largest of the two. In other words, here's a mathy thing, W log, right? Assume that, say, A is greater than B. There we go. What does W log stand for? Do you know? Yeah. Without loss of generality. In other words, it says, I'm going to state this assumption so that the proof is going to be easier to present. And it's without loss of generality because this assumption doesn't kill the entire overall theorem, right? And so without loss of generality, you can assume that A is greater than B, or at least greater than or equal to, right? Greater than or equal to. Why? Well, the GCD doesn't change if you swap A and B, right? So without loss of generality, assume that A is the biggest one because if not, just go ahead and swap them around and it doesn't change the algorithm, okay? The same GCD of 77 and 97 is going to be 97 and 77, right? That's still going to be 1, okay? And that allows you to focus on one input, right? So if not, then swap them. Right? So you can do little tricks like this to make sure that your analysis is a little bit simplified, okay? Step 2 is identify the input size. Right? So this is a subtle but important and maybe tricky, right? And we're going to look at one instance in which it's tricky. But if the input is a collection, right, then what's the size? If I have a set of 5 elements, what do we call that? The size of a set is for those of you in 235? No? If I've got a set S, and I put lines around it like that, that's the size of the set. What is that called? Cardinality. Right? That's the technical term. Right? Don't worry about it. It's the size. Size is the number of elements in the collection. It's not necessarily a set, right? It could be a dictionary, it could be a map, it could be a list, et cetera, right? If your input is a matrix, right, or an image, right, you could consider both dimensions, right? So, for example, you'd have an n by m matrix, or an n by n image that you need to rotate or translate into from RGB to CMYK for printing or something like that, right? Again, without loss of generality, right? Only consider one. Only consider one. Right? Suppose that n is greater than or equal to m. Then consider n, excuse me. Right? Why? Because if you've got a rectangular image, you can go ahead and pad it out with a bunch of useless pixels at the top to make it a perfect square. And now it's n by n. Now, do you consider n squared to be your input or n to be your input? Either or. You're going to get the same basic analysis. So keep it simple with one number, n. Right? With a matrix, you've got the same story. If you've got a non-square matrix, you can always pad it out with zeros. Right? And most operations will be the same. Just keep things simple, okay? But the one that's tricky is going to be the Euclid's GCD algorithm. What if the input is a single integer or single number? Right? Now what's the input size? All right, so for this, we're going to get a little bit mathy, okay? So is there a difference between the following numbers that I'm going to write down here? 1, 2, 3, 123, and 4, 8, 7, 6, 3, 2, 1, 5, 7, 3, 4. Right? Is there a difference between the size of those two numbers? Hopefully you would say yes, right? If I said, how many pennies do you want, which one are you going to, or how many dollars do you want, which one are you going to choose, right? If I say that you have to give me that many dollars, which one are you going to choose, right? Hopefully we know that it makes a difference, right? But what is the difference? How do we quantify that difference? You could think about it in terms of the magnitude, right? But did I have to write down 123 things for that first number? No. Did I have to write down, what is that? 48, what is that, billion? Did I have to write down 48 billion things to represent that second number? No. How many things did I have to write down for this first number? 3 digits, right? We call those things digits. How many things did I have to write down for the second number? Ignore the commas. That's just for formatting. What is it? 9, 10, 11? 11 digits. Right? So, the input size of a number is what it takes to represent that number. On a piece of paper, 2,000 years ago for Euclid, or in a computer nowadays. Right? So does a computer operate on digits? No. A computer operates on what? It is called digits. Right? But we don't like that, and they didn't like that in the 50s or 40s or wherever they came up with that number, or that name. So what did they rename it? How are numbers represented in a computer? Hopefully we know. Binary digits would be bits, right? Instead of digits. Okay? So my question is, how do we know how many bits are required to represent a number? So let's go ahead and couch it in terms of digits instead, because that's easier to understand. What if I gave you, if you had this many digits, this many digits, say 1 digit, then the maximum number you can represent is ... If I gave you 1 digit, now 10 fingers, 10 toes, so we're in base 10 now, then what's the maximum number that you can express? 3? No. 9. Thank you. Right? Hopefully we do know basic math. Now, what if I gave you 2 digits? 99. Right? And hopefully the pattern starts to become clear. 999 if I gave you 3 digits. If I gave you 4 digits, well, then now you can have carryover, and you can do 9,999. ... If I gave you k digits, what is the maximum value that you can represent? Well, 99, ... 99. How many 9s are going to be here? K of them. How do we express that in terms of k? How did we express it here? This is going to be 10 minus 1. This is going to be 100 minus 1. 1,000 minus 1. Right? How do we incorporate that digit over here? It's going to be 10 to the k minus 1. Well, oh, the minus 1 is there. Why? Because we have to start at 0. Right? Okay. Take this and now solve for k. Right? So what is the maximum number that I can represent with k digits is going to be x. Right? And that's going to be 10 to the k minus 1. I need to know how many digits it requires to represent x now. In other words, I'm just going to solve for x. So x plus 1 to the other side, right, is equal to 10 to the k. How do I get rid of that 10 and solve for k now? Logarithms. Right? Log base 10, right, of x plus 1 is equal to k. Right? So in other words, the logarithm function, one interpretation of it is the number of digits it takes for base 10 for you to represent that number. Should we even be talking about the natural log? Remember, the natural log is base e. Have you ever heard of a system with 2.71 symbols? Right? Why is it base 10? Because we've got 10 symbols. 0, 1, 2, ... 9. Why would it be base 2? Because we only have 2 symbols, 0 and 1. But if we go with the natural log, which is only natural because of the first derivative, calc folks, right? Is there anything natural about having 2.71 symbols? 0, 1, and then only like a third of a 3 or something like that. It doesn't make any sense. But it does make sense mathematically. Right? You can talk about non-integer base systems. It's weird, but and you can't write them. Just like you can't draw a fifth-dimensional triangle or something like that, right? You can draw a projection of one, but you can't draw the actual fifth-dimensional object, okay? Now let's go back and redo this all for, instead of digits, what if I gave you bidgets or bits, okay? Now, how does the analysis change? If I gave you 1 bit, it could be 0 or 1. What is the maximum number that you can represent? Well, just 1 bit. 0 or 1. Just 1. Now, if I gave you 2 bits, I would make them all 1, and that is equal to... This is 2 plus 1, so this is 3. Right? If I gave you 3 bits and make them all 1 to maximize it, that's going to be what? 7. 4 bits is going to be 15, ... If I gave you k bits, right, that's going to be 2 to the k minus 1. Right? In other words, it's exactly the same before, but instead of base 10, it is now base 2. Do the same thing. If I have x, the maximum number that I can... how many bits does it take to represent x? Well, 1 goes onto the other side. And now how do I get rid of that 2? Take the log base 2 of x. In other words, k, for all intents and purposes, is going to be log base 2 of x. Okay? So, if your answer to what is the input size of... Oh, here, I've lost the Euclid's algorithm here. Assume that a is greater, and that's our single input. What is the input size of that number? It's the number of bits required to represent that number, or the number of digits, or the number of 2.71 symbols, right? Or hexadecimal, base 16, whatever you want. It doesn't really matter because of the change of base formula. Log base a of x is equal to, if I want to change this to log base b, I can do that simply by taking out a constant with respect to a. This is some constant log base b of x. Right? That means that you can change from binary to hexadecimal to decimal to an alien base 32 or base 33 system in the future when we meet the aliens and they've got 33 fingers and toes. And so their natural way of counting is base 33, right? Base 33, or the change of base formula. All logarithms are the same to within a constant. Okay? So the takeaway from this is, what is the input size? The number of bits required to represent the number. Right? In other words, log base 2 of n. There we go. Where n is the number. I'll go ahead and write it as x, though, because x will make x the number. Okay? And because we're all self-respecting computer scientists, anytime that we write log, it is implicitly base 2. Right? So if you just see log, you know all logs are the same to within a constant. So my log, because I'm a computer scientist, is base 2. If you go over and you put on your calc hat, then your base is the natural base, e. Right? If you start counting with your fingers and your toes, then you are a normal person and you are counting base 10. Right? It doesn't matter to us because you can change it. Okay? So that's the input size. Ultimately, the third step here is going to be, again, you're going to want to focus on one thing. When you think about the elementary operation that is required for this algorithm, which one do you want to focus on? You're generally going to focus on the most expensive, the most common, or the most relevant operation. You're not going to focus on, you do not consider, for example, operations necessary for the control structure the algorithm. For example, all those with a for loop, for int I is equal to 0. I'm not going to count that initial that variable declaration and initialization, nor am I going to count I as less than n as a comparison, because that's necessary for the control structure of the algorithm, right? Let's go back to our example here with linear search. And I'm not going to count anything that's in this that's necessary to actually execute this for loop, because we are doing work inside of that for loop. Anything that we do outside the for loop here, or for the for loop, is going to be compounded by the complexity of whatever we're doing inside the loop. So I'm not going to count anything that's required for the control structure of the algorithm. What else am I doing in this algorithm? I'm outputting something, but is that the most common thing to do? Nope. In fact, you only do it once for the entire algorithm. What are you doing over and over and over again? The comparison on line 2. Right? So another tip, make sure that you are numbering your pseudocode so that you can make reference to a specific line. Right? Okay. So for search-based algorithms, maybe you want to consider comparisons. Right? So examples, comparisons. What if I'm doing some mathy stuff? I'm doing some matrix operations or something like that. You can consider arithmetic operations. For example, additions and subtractions, or multiplications and divisions. Right? I'm just going to shorthand it there. Now, why did I group those two with a slash there? An addition and a subtraction. Are those really any different? What is a subtraction? You're adding a negative. You negate one, and then you add it. So it's really just an addition. What about a division? How is a division a multiplication? You're multiplying a fraction or the reciprocal, right? 1 over x to divide, and then you're doing a multiplication by the reciprocal. So those are basically the same operations. Between those two groups, though, additions and subtractions and divisions and multiplications, which one is probably more expensive? Multiplications and divisions. Why? Because one you could do a multiplication with an iterated addition. 5 times 10 is 10 plus 10 plus 10 plus 10 plus 10. I think I did 5 times there, right? You're doing a certain number of additions. So one is more complex than the other because you can do the other in terms of the first one. Okay. What about linked list stuff? Right, linked list operations. What was the most expensive? We started out this entire discussion with an example of the get method here. And it was super slow on the linked list. It was lightning fast on the array list. Why? What operation are we doing with the linked list? We did nodes, right? We started at one node, went to the next node, went to the next node, went to the next node. In other words, node traversals. Right? This also equally applies to trees, which we'll be looking at next, and graphs more generally. So if you have a graph and you want to do an operation on a graph, you've got a bunch of vertices, nodes, and you've got a bunch of edges connecting them, right? Going from one node to another node, that's your operation. Right? It all depends on what data structures you're using, what your algorithm is doing, what you want to analyze it with respect to. Right? Examples. Right? Finally, you do an analysis. Okay? The analysis is probably going to mean that you are doing some sort of a resource function. Right? And let me go ahead and cut and paste this. You analyze how many times the elementary operation is executed with respect to n, so that you can come up with a function of n. Right? You come up with this resource function, and this should not be bullet pointed. There we go. There we go. And what does it look like if I do it like that? There we go. Nice. So I labeled it as t, and it has a domain and a codomain here. Input sizes are a resource measure, and a resource measure such as time. Okay. Do we know those symbols there? If not, let's review or preview if you're not been taking 235. So let me go ahead and rewrite it over here. This is a function mapping this domain to this codomain. Okay? you can think of it as the first quadrant in the Euclidean plane here. Now, generally, functions will map reals to reals, right? This symbol right here is the real numbers. 1, 1.5, pi, right? Any fractional value, right? So let me annotate this, maybe. This is the positive reals, right? This is, does anybody know what that is? What is n? What elements are in that set? Oh, no? So those are the natural numbers. That's why it's n. 1, 2, 3, dot, dot, dot. But also, I left myself some room here. What else is in there? Where do we start the natural numbers? Oh, no? Oh, I thought everybody takes 235 along with 156. Is that not the case? Yes? Okay. So the natural numbers are 0, 1, 2, 3, 4, 5. In other words, the non-negative integers. Why do we include 0? Because we need an additive identity. X plus 0 is equal to x, right? So these are the natural numbers. Right? So why do I limit my domain and codomain here? Right? What is this modeling? This is modeling the input size. Have you ever heard of an input size of -5 elements? Nope, that doesn't make any sense. Have you ever heard of an input size of 3.5 elements or 3.5 elements? Nope, that doesn't make sense either. So we're going to restrict our resource function here to natural numbers in the domain and then positive reals in the codomain, the time that it takes you. Why do I focus on the positives? Right? Have you ever heard of an algorithm that when you run it took -3.8 seconds to execute? In other words, you started your computer and then 3.5 seconds in the past, you had your answer. Kind of trippy. That's time travel, right? Maybe it's possible, maybe it's not. In any case, we're not going to model it. So that's why our resource measure here is going to be a function, right, of natural numbers to positive reals. For all intents and purposes, you can consider it as monotone increasing functions, right? N squared, n, 2 to the n if it's really, really steep, right? But it all comes down to an art, right? It may require some art, some summations, like a formula, solving a formula, all right? It might come to some sort of math, right? In general, however, you want the worst case scenario. You want to provide an upper bound on your analysis because you want to know, in the absolute worst case, how is this algorithm going to perform, okay? So that's the 4-step process in detail. Let's do it for our linear search algorithm right here. Before we do that, let me go ahead and get rid of that so that I've got some more room. And yeah, I'll put it over there. Okay. So step 1, what is our input? And again, should it be the key or should it be the collection? Probably the collection. Hey. 2, what's the input size? It's encoded in the input. N, right? The number of elements in it. 3, what is our elementary operation? Well, we've already identified that in calling out to our example here, the comparison on line 2. Right? So, comparison on line 2. 4, and I've skipped the 5th step of this all because I want to get some more examples before we get to asymptotics. How many times is that executed? How many times is line 2 executed with respect to the input size in the worst case? Remember, the best case is you find it immediately, right? And you only had to do one comparison. The worst case, however, is when you had to compare every single element all the way to the end, right? And then you found it at the last place that you looked, or you found that it didn't exist and you end up returning phi. So an easy answer here is going to be what? N. And then a preview of step 5, it's going to be order n, because it's a linear function. Okay. Let's do something harder. Let's see. Linear search. Let's go with sorting functions here. Where's my selection sort? There we go. Now, if we had more time, we might actually develop this pseudocode from scratch. But I'm just going to go ahead and jump to the end here. And this is our old friend selection sort. Remind me quickly, though, how does selection sort work? So let's look at an example here, at least on the first iteration. All right. It's going to go through and put the minimum element here at the front. It's going to have to go through and find the minimum element first. So one comparison, 2, 3, 4, 5, 6, 7, 8, 9 to find the minimum element. Then what is it going to do? It's going to take that minimum element and swap it over here so that this is 0 and this is now 42. Right? On the next iteration, right, and this is the outer for loop right here, what's it going to do? It's going to look at the remaining elements here and find the minimum among those and place it at the second position. So what's the minimum element here? 2, right? And so it would end up putting 2 over here and 4 over here. Okay. This is sorted at this point. You continue in that regard to the rest of it. At the end of the day, you stop short. You only go up to n-1 because if you've sorted the first n-1 of them, guess what? The last one is exactly where it needs to be. Right? If you need a review on a more in-depth review on selection sort, you can go ahead and watch the videos or go back to the Computer Science 1 textbook. Okay? But let's analyze it. Let's go ahead and get rid of that. Where are we? There we go. Let's get rid of this. Same 5-step process, truncated to 4 steps. What's the input here? Same answer as before. A, the collection. What is the input size? It's going to be n, the number of elements in the collection. 3, what is the elementary operation? So here is where you have a choice. Right? I am doing a comparison here on line 4. But I'm also doing comparisons up here in my for loop, right? I'm iterating through while my variable I is less than or equal to n-1, right? I'm adding. Do I pay attention to what is necessary for the control structure of the algorithm? No. Likewise for the inner for loop here. Well, what about this this assignment here? Maybe, but I've got a for loop here, and I'm doing stuff inside that for loop. So this is definitely not the most common. Right? Neither is this, because you don't do it on every single iteration. You check here. Now, I am doing another operation somewhere else that would be a perfectly valid answer. Swaps. Right? If you were put on your engineering hat for a second and tell me about flash memory, right? What is the most expensive thing with respect to memory? Not reading, but writing, right? If you write to your flash memory, that degrades the memory faster than if you just write once and then you read only from it, right? I/O is way more expensive than CPU time, right? So you might say, well, okay, I've got an embedded system application here. I want to optimize for swaps rather than for comparisons, because comparisons are lightning fast on this embedded system. But memory I/O, that's way more expensive. That's my bottleneck. And that is a perfectly valid engineering concern. In fact, we usually, every so often, Garmin will come in, a representative from Garmin. They do a lot of embedded system stuff. And one of them always tells a story about how they chose a bad sorting algorithm, say bubble sort or something like that, which is slow, but it minimizes the number of swaps, minimizes the number of memory reads and writes. They were willing to take a hit on the time because their bottleneck was memory, right? They had a limited amount of memory, and their memory was slower than their actual processing time, right? Which is true generally. So they wanted to focus on this one instead of this one. There's no right answer. There's no wrong answer. Right? I mean, there's some obviously wrong answers, like whatever you're doing in this for loop up here, right? But both of these are perfectly valid answers. They just give you a different analysis. Right? Let's go ahead and stick with the comparison on line, what is it? Line 4. Okay. Now, step 4. That's where the art comes in. Okay. How many times is line 4 executed with respect to the input size? That's where we're going to have to come up with some sort of a summation here, right? So first of all, on line 4, just focusing on line 4 by itself, that block right there, how many comparisons do I do? Just focusing on those 3 lines right there. 1, right? So let's go ahead and start with 1, and this is line 4. Now we've changed the question. Treat this as one big block. And ask yourself, how many times is that block executed with respect to the input size? Well, it's executed for j running from I plus 1, I plus 2, I plus 3, I plus 4, ... up until n, whatever that is. That's a summation. For j running from I plus 1 up to n. So this is 1 plus 1 plus 1 plus 1. How many times? Let's worry about that when we solve the summation. Now I have this block right here. How many times is that block executed with respect to the for loop that it's inside of? It runs from I being 1, 2, 3, 4, 5, all the way up to, and including, n minus 1. So that's another summation. I running from 1 up to n minus 1. Right? This entire thing was on block 3, and then the entire thing was on block 1. Block 1, line 1, whatever you want. Right? Okay? So now I've got this nice expression right here. Let's go ahead and cut and paste it. There we go. Copy. No, I don't want the entire thing. Ah, come on. Copy. Right? And paste. Okay. Go ahead and get rid of this thing right here. There we go. Ah. Move you up here. Okay. Let's solve it. Right? This is a summation within a summation. If you're not good at solving summations, that's fine. Get some practice. If you want to verify your answer at the end, guess what? Wolfram Alpha is your friend. Wolfram Alpha will solve summations. You just have to know what syntax to use. Okay. Let's focus first on this inner summation right here. Let's get a handle on that. Right. Oops. I can move that over here. No, I want to copy it. Come on, copy. Paste. There we go. Let's get a handle on that. Right. What is this? This is 1 plus 1 plus 1 plus ... plus 1. How many 1s are there, though? We started it from j, running from I plus 1, right? I plus 2, I plus 3, ... up to n. So are there n 1s there? Nope. We don't start from 1. We start from I plus 1. Right? What if we did start from 1? 1, 2, 3, 4, 5, ... up to I plus 1, I plus 2, ... up to n. And we just did 1 plus 1 plus 1 plus 1 plus 1, ... plus 1 plus 1 plus ... plus 1. Right? Now, if I had started at 1, your answer would be easy, right? There are n of them. We didn't start there, though. Where did we start? Right here. That's what's up here. So how many things are there over here that are not included? That one's easy, too, because you start at 1 and go up to I. So how many 1s are there here? I of them. So if you have, in total, you have n ones, right? N ones right here. But you take off I of them, what is it going to be? N minus I. Right? So this is equal to, outer summation remains the same, of n minus I in parentheses. Okay? Summation of sums is equal to the sum of summations. So I can break this up further. This is two sums. I is equal to 1 up to n minus 1 of n minus the summation of I equals 1 up to n minus 1 of I. Okay? Give myself some more room by getting rid of all this. Sum of summations is equal to the summation of sums, right? You can just break that up. Okay? Now what about the first one? That should be easy. N plus n plus n plus n. How many times? 1 up to n minus 1. So n plus n plus n plus n, 5 times would be 5n. N plus n plus n plus n, 10 times would be 10n. How many times am I actually doing it? N minus 1. So this is n minus 1 times n. Okay? What about the second one here? This one is the tricky one. And for that, I'm going to go ahead and put in a good word to our friend Gauss. Gauss's formula. If I go from I equals 1 up to n of I, that's equal to 1 plus 2 plus 3 plus ... plus n. So the apocryphal story is that Gauss was annoying his instructor or whatever, and so his instructor gave him the busy work of, all right, write down all the numbers 1 to 100 and sum them all up, right? And thinking that it'll take him, oh, that'll keep you busy for a half hour or something like that. And he immediately answered what the answer was. What is the answer? 50 times 99, right? 5,050. There we go. Thank you. 5,050, right? And how did he come up with it? Well, he came up with this formula. N times n plus 1 over 2, right? That's a classic example that is used to introduce induction. So if you've done proof by induction in 235, yes? Say what? What? You're talking about it right now? Okay, induction? All right. Usually the first inductive proof is a proof of Gauss's formula right here, right? Now, I don't have Gauss's formula here because I start at 1, but I only go up to n minus 1. So you could take and subtract off of n minus 1, right? Or you could just take n minus 1 and substitute it in up here for n, in which case you get what? If I substitute n minus 1 into n, and n minus 1 plus 1, then that comes up with what? N minus 1 on the first one, and n minus 1 plus 1 cancels each other out, n over 2. That's just an application of Gauss's formula. Now, the second one is half of the first, so what am I left with? After rearranging everything. N times n minus 1 all over 2. If you want to, you can expand that out. 1/2 n squared. Oops, not n to the n. It's not that bad. Selection sort is bad, but it's not that bad. Right? Minus 1/2 of n. Okay? I put the 1/2s out in front because, again, what are we going to do at the end of the day on step 5? We're going to ignore lower order terms. Which one is the most important term here? The first one or the second one? N squared or the linear term? N squared, because that's going to be the most expensive. Now, what about this constant sitting out front here? Do we care about it? No. We throw it away because you can just improve your hardware and that constant changes. Right? And ultimately, we're left with that it is going to be an order n squared sorting algorithm. Terrible. Terrible, terrible, terrible. Right? A slightly better sorting algorithm. Let's look at another example. Again, this is going to be mostly by example because when you get into math and mathy stuff, right? It's really easy when somebody's already done the math first. How are you going to be the person that does the math first before anybody else, right? Well, you only ever see the final proof. You didn't see the 50 or 60 different proofs that they went through, attempts that they threw away because it didn't work, right? When you're doing math and you're trying to discover a proof, right? You're going to have a lot of failures. Failures are not publishable. So don't, if you're trying to prove something in 235 or something, right? And it's not working, don't get down on yourself, right? It took a mathematician 50 years to come up with that first proof, right? It took us thousands of years to come up with the concept of zero, right? All of our math ideas are built on the shoulders of giants, right? So don't get down on yourself if you can't find the proof immediately. There are plenty of open mathematical questions out there that nobody knows the proof for, right? And that we're still working on. But let's go ahead and keep it simple and only look at stuff that we can do easily, right? If we just walk through it. This is insertion sort. And if you haven't seen this one, let me walk you through at least one iteration. Let's take our array again here. Okay. Now, insertion sort works not by going through and selecting the minimum and then swapping it. It works by assuming that we've got a sorted list already. And so where is your starting point? The first element, 42. If I ignored everything else, right? I've got an array of size 1. By definition, it is sorted, right? Now what we're going to do is we're going to ignore. There's no way. I guess I could highlight and then, let's see, my highlighter here. I could gray this stuff out, right? Right. Ignore that. Right. Now we're looking at an array of size 2 here, right? And we know that this part is sorted because that's where we started out with. But now this part, that's not sorted. What we're going to do is we're going to take this and we're going to insert it where it needs to be. So we end up with what? 4, that's out of order with 42. So we swap those. And then 4 and 42, they're now sorted. Let me go ahead and take that over here to the next one, the next slide, or whatever you want to call these things. Right? We've got 4 and 42. Right? This is now sorted. And we're going to consider the next element here, 9. Right? We want to insert it where it needs to be. So our first step here is going to be compare it to 42, right? And it's out of order, so we swap it. Right? And you can imagine what that looks like initially. There we go, 9 and 42. Now we still don't know if it's been inserted in the correct spot yet. So what we're going to do is we're going to compare 9 to 4 over here, right? Swap. Do I swap those? Nope, they're in order. So by the end of the second iteration, we already have a 4, 9, and 42 array here. Right? It looks something like this. Right? The next element that we need to insert is going to be another 4. Okay? So 4 is our next element. We compare it to 42, swap it, swap. We compare it to 9, swap. And then we compare it to 4. How should we break ties? 4 and 4, or 4 and 4. Is there a difference? No. So don't swap. And you're done. What I have now is 4, 4, 9, and 42. There's my new sorted array. Okay? Now here's where, 2 more iterations maybe. 102. Do I end up swapping it? Nope. It's where it needs to be. The last one that I'll cover is 34. Okay. So how many swaps or how many comparisons am I going to make here? 1 to see that it needs to be swapped with 102. Another one, 2, to see that it needs to be swapped with 42. And then 3 to see that 34 belongs right here and it should be inserted right here. So I end up with 4, 4, 9, 34, 42, 102, right? With only 3 comparisons. How many comparisons did I have to do for 102? 1. How many comparisons did I have to do here for 4? 3, right? 1, 2, 3. How many did I have to do for 42? 1, and then, was it, nope, sorry, just 1, right? Why did I have to swap that? I don't think I did swap it. Oh, that's right. I erased it. No, that's why, right? In other words, it's adaptive. Sometimes it takes only one comparison. Sometimes you might have to, for example, if I needed to insert 0 next, I would have to shift that all the way down to the end. In which case I have to do I minus 1 comparisons if I have I elements in this array so far, right? That's what the pseudocode is doing here. Let's annotate it, right? So initially, we skip 1, or I equals 1. Why? Because an array of size 1 is sorted. Right? We go all the way up to n. Why? Go to n because the last element needs to be inserted. Right? What are we doing inside that for loop? Right? Well, first of all, what we're doing is we're save the ith element to a temp variable that I call x, just so that I don't have to update any other indices. I'm just here's my x. Here's the element in each one of these iterations. That was my x, right? So 4, 102, 34, etc. Right? Then I initialize j to be I, right? I. Why? Because I'm looking at the ith element right here, right? And I've got x now, and I need to know whether or not I need to shift it down, shift it down, shift it down by doing a bunch of swaps. Okay? That's where this while loop comes in, right? While x needs to be shifted down, right? Shift it. All I'm doing here is putting into ace of j plus 1. In other words, it looks something like this, right? This one is, all it's doing is it's taking ace of j and moving it over to ace of j minus 1, plus 1, excuse me, right? It's shifting stuff over to make room for x in the end. Right? And what do we do at the end? We insert x, in other words, ace of j, or ace of I, excuse me, where it needs to be. Okay? Now take a look at what we're doing with the while loop here. What is this condition doing? While j is strictly greater than 1, do I want my j to fall? J is going down, j is going down, j is going down. Where do I stop? At the first element. Do I want j to fall off the end of this array? No. So that's just a bounds check right there. Necessary for the control structure of the algorithm. Ignore it. This is my real comparison right here. I'm taking this element and I'm saying, well, does it need to be here? Does it need to be here? Does it need to be here? ... Okay? So now this one is going to be a little bit more complicated to analyze. All right? Let's insert a clean version of it. There we go. So step 1, step 2, step 3. Fast forward. Step 1. What is the input? The collection. What is the input size? The number of elements in the collection. Step 3. What is my elementary operation? This comparison right here. All right? Here I don't have a nice clean for loop that I can set up a summation for, do I? In fact, when we ran through this, we saw that it was adaptive. Sometimes you get lucky, right? And you only have to do one comparison. Sometimes you get unlucky, and you have to do way more comparisons. Sounds kind of like linear search. Which one should we focus on? Getting lucky and only having to do one comparison? Or getting unlucky and having to do all the comparisons? Let's look at the worst case scenario. All right? So let's focus on this inner while loop here. The outer while loop, that's easy. I running from 2 up to n, right? Focus on the inner while loop here. What is the worst case scenario? Let's visualize it, right? So you've got the ith element here, a sub j, or a sub I, excuse me. Right? And you've got how many elements before it? Well, if this is the ith element, then you've got I minus 1 elements to the left of it. Right? You don't compare a sub I with itself, right? That would be useless. So we only compare it with this element, maybe this element, this element, this element, dot, dot, dot. In other words, all of the elements, right? The worst case scenario is when we have to shift a sub I all the way down. Right? How many comparisons do I make in that case? Well, how many elements are here? A sub 1, a sub 2, dot, 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 a sub I minus 1. So how many elements are there to compare to? I minus 1, right? Exactly what I wrote up here, right? I minus 1. So in the worst case, again, best case, there's only one comparison. But the worst case is going to be I minus 1 comparisons for this block right here. Okay? Let's stick with the worst case scenario, I minus 1. Right? We've got a summation on the outer for loop here. So let's write that down. There's a summation I running from, what was it again? 2 up to n. 2 up to n of, and how many comparisons do we do in the worst case scenario? I minus 1. There we go. And now we just have to solve that summation. Fast forward, throw it into Wolfram alpha, right? But otherwise, the same trick as before. In fact, the same tools as before. Summation of the summation of sums is equal to the sum of summations. So you can break this up into I is equal to 2 n of I minus summation of I running from 2 up to n of 1. Okay? That looks familiar. Kind of familiar. Where are we? I have to go back that far? Okay. Gauss's formula. Come on. Come on, copy. Gesture base. There we go. Copy. All right. Fast forward, fast forward, fast forward. There we go. Paste. I should have just put that into LaTeX, and so I could cut and paste it anywhere. Right? Okay. How can we apply Gauss's formula to this thing now? Just the opposite problem as before. We're not stopping short. We're skipping 1. Right? So in other words, it's 2 plus 3 plus 4 plus 5 plus dot, 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 n. Right? So all I need to do is focus on these terms down here. And in other words, this thing right here minus 1. All right? That's n times n plus 1 all over 2 minus 1. That's the first summation. The second summation should be really, really easy, though. 1 plus 2 plus... Oh, sorry. 1 plus 1 plus 1 plus 1 plus 1. How many times? N times, except that I start at 2. So it's going to be n minus 1. Algebra, algebra, algebra. What are you going to ultimately come down to here? Yep, you're going to come out with some coefficient here, probably 1/2 of some sort, times n squared plus some other coefficient here. In fact, I'll name it a, b, n plus some value c here, right? I don't even care what they are, right? You could put them into Wolfram alpha and find out exactly what a, b, and c are, right? If you want to. But at the end of the day, what are we going to do? Ignore lower order terms. Ignore constants sitting out front. And only focus on the most important term here. Right. One last preview here that we'll pick up next time is going to be quicksort. Quicksort. we remember how it works? If not, I'll show you, give you a really quick preview here. But otherwise, that looks completely different, right? There is a loop, kind of. The loop is hidden in the recursion. We've got recursion now. How do we go about analyzing recursive algorithms? There is this subroutine here called partition. Somebody asked about it on Piazza, so if you want it, it's right here. This is in the Computer Science 1 textbook. There's the partition. All it's doing is it's choosing what's called a pivot element, and it's putting things to the left-hand side or to the right-hand side. For example, oops, I didn't mean that. I meant that. Right. And let's insert that same array again. Where is it? There we go. Here's a preview of how it works. You choose a pivot element, say 42. And what you're going to do is you're going to go through every single one of these other elements, and you're going to put things that are less than 42 to the left, and things that are greater than 42 right, to the right. So 4 is less. I'll put it over here. 9 is less. 4 is less. 102, that's greater. I'll put it over here. 34 is less. I'll put it over here. 12 is less, so I'll put it over here. 2 and 0. Now, where do I put 42 at the end? Right here. Right? This is called a pivot element. Right? And you pivot around it. Okay? I've partitioned it so that everything over here is less than the pivot element. Everything over here is greater than the pivot element. Sounds kind of familiar, binary search kind of thing, right? And then I repeat. I recurse on this part, and I recurse on this part. Tell me about this part, though. 102. Do I need to do anything else with it? Nope. By definition, an array of size 1 or 0 is sorted. Right? What about this thing right here? Right? 4, 9, 4, 3, 4, 4, 9, 4, 34. What else is there? 12, 2, and 0. That wasn't 20, that was 2 and 0. I choose a new pivot element here, 4. And I repeat. Everything greater than it, 9, 4, 34. 12 is greater than 4. 2 is less than 4, 0. And then I put 4 where it needs to be. Recurse on this, until you get to your base case of one element, right? That's where this L and this R come in, right? When you've got, while they're strictly less than each other, in other words, while you've got an array of at least 2 elements, maybe more elements, but at least 2, then continue your recursion. You partition by putting things less over here, greater over here, and then you recurse on the left partition and the right partition. Don't try to program that from scratch in your lab on Wednesday, right, tomorrow. Either use our pseudocode from a Computer Science 1 textbook, or go to a reputable site. Wikipedia is reputable, I'd say, and adapt their code. Don't go to some garbage like awesomecoder.india.com or something like that, whatever, right? Not even Code Academy, I would say, is good. No, I don't think that they would have published anything. But like the usual clickbait top hits that are just content farms, they're probably going to have some bugs in them, right? And good luck debugging those. You basically have to go through, understand 100% what they're doing, and then understand even better what they were doing than they understood in order to fix their bugs. Bug fixing requires a cognitive load far greater than if you just wrote it from scratch yourself. Trust me. All right. Again, those both are in Computer Science, the Computer Science 1 textbook. All right. I'll see you on Thursday.